Okay, so good day. This is our last lecture in static electricity, and we're going to introduce some relatively new concepts, and you know, hopefully you'll understand fully what's going on. Now we're going to introduce the concept that inside a conducting surface, inside a conducting surface, the electrical field is zero. So that is, you are protected if you're inside a conducting uh, uh, object. So if you're in the center, or if you're inside the conducting uh, object, you won't get any shock. The electrical field is zero. And Michael Faraday, one of the earlier physicists, proved this. And he came up with what is now known as the Faraday's cage. Okay? So what we're saying is that electrical field inside a conducting surface. So this is a Faraday's cage. So it is made of conducting material, and someone or something can go in the center of this, or can go inside. So what we're saying is that the electrical field is outside. The electrical field in the center of this cage is zero. So you are essentially protected from any type of charge. Okay? So, you know, in circus and, shows, people will do these so-called tricks to show, they'll get a high voltage charge, and someone will stay in the center or inside the cage, and they won't be shocked. They will be protected. Again, the electrical field inside a conducting surface is zero. Okay, Michael Faraday did a lot of work on that particular experiment. So the practical use for something like the Faraday's cage, if you have any electrical equipment that you want to protect, your cell phone, any expensive gadget, you can put these gadgets inside uh, a metal case, and it will protect these electrical equipment from damage, from electrical surge and stuff like that. So that's a practical use of the fact that the electrical field uh, inside a conducting surface is zero. All right, so you can protect delicate electrical equipment by placing them in metal cases, so such as this. So if you have a metal case and you want to put your cell phone and other expensive gadget, you do that, and they'll be protected because the electrical field inside a conducting surface is going to be zero. You cannot get an electrical field inside these um, these conducting cages. Um, there's another concept that we're going to introduce, and that is electrostatic equilibrium. And say you introduce a charge on a conductor. If you introduce a charge on a conductor, it's going to take a little time for the charge to redistribute itself until there's no more movement. Initially, say you introduce if you introduce a bunch of electrons on a conducting surface, the electrons going to repel themselves once they get on the surface of this conductor. They're going to repel themselves until there's a position. They're going to repel themselves until there's a position where there's no more movement of electrons. Okay, because they're all at a certain distance so that the repulsive force is minimal. And that is what we call electrostatic equilibrium. So when conductors are at electrostatic equilibrium, there are a number of things that we observe. Okay, again, when we talk about electrostatic equilibrium, we're talking about the charge redistribute themselves. The charge are going to redistribute themselves until there is no more movement of electrons. Okay, so again, remember, electrons are going to distance themselves from each other. Okay, so once the distance is adequate and there's no more movement of electrons, then we call that electrostatic equilibrium. When we have a conductor at electrostatic equilibrium, the electric field from the surface is always directed perpendicular to the surface of the conductor. And another thing that is observed is that the electric field is strongest at location where the object is most curved. And I'm going to show you that. Okay? So this just show you that if you have a conductor, and this conductor is at electrostatic equilibrium, that is, the charges are not going to move. The electrons are not going to move. They already distance themselves from other electrons, and they're spaced out, as much as they're going to space out. The electrical field inside the conductor is going to be zero. The electrical field inside the conductor is going to be zero. Okay? And also the electrical field, and we draw the electrical field lines. The electrical field is perpendicular to the surface of the conductor. So those are two phenomena that we need to get. So the electrical field is going to be perpendicular 90 degrees to the surface of the conductor, and then because this conductor is in electrostatic equilibrium, the electrical field is zero inside, zero. So you don't have to worry about getting shock or anything like that once you're inside. Okay. All right. So again, just to stress, when we say something is in electrostatic equilibrium, there is no net motion of charge occurring within the conductor. The conductor is said to be in electrostatic equilibrium. That means, if you introduce some charges, they're going to move around until they find a comfortable position where they don't have to move anymore. Okay? So when a conductor is in electrostatic equilibrium, the electrical field is zero anywhere inside the conducting material. It is going to be zero. Any excess charge on an isolated conductor resides entirely. So the charge resides entirely on the surface. Okay? All right. So again, when you introduce a charge to a conductor, so conductors they're easily polarized. So you can introduce some electrons. Free electrons going to move around freely inside the material. Okay, so any charge that is placed on the conductor gonna arrange themselves in a stable fashion, okay, until they're in a comfortable position and they don't have to move again. So we're stressing the point because it's important to understand. So for a conductor in electrostatic equilibrium, the electrical field inside the conductor is going to be zero. So you can protect whatever electrical equipment you have inside inside a conductor. Okay, the net charge is going to reside on the surface of the conductor, and then the electrical field is going to be perpendicular to the surface. And then when you have an object wherever you have an eye, wherever the object is curved, you're gonna have more electrons there, and you are more charged, and you're gonna have the electrical field is going to be strongest. And this is what we mean by that. So when a conductor is in electrostatic equilibrium, the charges are concentrated at regions of greater curvature. So at the corners, greater curvature. At the corners, greater curvature. Okay, as opposed to just on the side. What we're saying is that you're going to have more charge at regions with greater curvature. You're going to have more charge, and it's a simple mathematical fact, because if you were let's take these positive charge around this object. Okay, if you take the positive charge around this object, the charges are going to repel themselves. So the charges are going to repel themselves. So the force of repulsion is going to be, in this case, it's going to be from positive to positive. It's going to repel itself. But if you have, say, a curved surface, the force of repulsion between these two positive charge is going to be right here. But when you do the mathematics, the repulsive force is going to be less. Okay? The repulsive force is going to be less where you have greater curvature. And because the repulsive force is less, you're going to have more charges there. Because if the repulsive force here is very great, this positive charge is going to distance itself from this positive charge as much as possible, because the force is greater. But when you have a curved surface, you can work it out and show that the repulsive force is less. So the charge is going to crowd up. The charge is going to be more. So you're going to have more charges at regions of greater curvature, just because the force. And the same thing right here. Once you have, a curved surface, the charges are going to accumulate where you have a charge, where you have a curved surface. And it is, again, it's just when you do the resolution of the forces, you'll find out that when you have a curved surface, the repulsive force is going to be less. So the charges sort of bunch up. You have more charges. So if you have an object like this, the charge is going to be greatest where you have greatest curvature, greater curvature. The charge is going to be much the charge and the electric field is going to be greater or greatest where you have a curved surface. Where you have a relatively flat surface, you can see the charge, they space out more because the force pushing them away from each other is greater. Whereas when you have a curved surface, the force pushing the charges away from each other is less. So they sort of clump. The charges clump up. And you can represent that by drawing your electric field lines. So you draw your electric field lines showing a cluster, because when you have a greater density of your electric field lines, it tells you that you have greater charge, right? And again, when you have a positive charge, the electric field line moves away from the charge. Very important concept. When you have curved surface, you're going to have greater number of charges, greater number of charge, and then uh, you can use your electric field lines to show that, showing the same thing. And it has to do with the resolution of the force. Okay, so if you take these two charges, they're going to repel each other. Okay, they're going to repel each other. So the force is going to go that way, the force is going to go that way. But you can resolve this force. You can resolve this force into its vertical and horizontal component. But the fact is that when you have a curved surface, the repulsive force the repulsive force is going to be less. So if the repulsive force is less, the charge is going to clump up, as opposed to a flat surface. The repulsive force is going to be greater, so the separation of the charge is going to be much greater. And you draw your electric field lines, show them closer together, telling you that you have greater charge along curved surface. And then when the surface is not as curved, then the charges are a little bit more spaced out. Okay, so all it has to do with the force. Okay, when you have great curvature, the force is going to be less. So therefore, you're going to have more charge clumping together. Okay, so and you can draw your electric field lines to represent just that. All right, so we're going to move on now to lightning, and why we get lightning. What is lightning? So lightning comes from what we call storm clouds, and these storm clouds are in the atmosphere. And let's look at this one. So you have a storm cloud, and cloud is just a mixture of water vapor, ice, and other air molecules. Um, but when these water vapor and uh, frozen material, when they come into the cloud and they strike they other um, water vapor or ice in the cloud, the electrons the electrons are sheared off. And when you have a storm cloud, the bottom surface of the storm cloud is usually negative. The bottom surface of the storm cloud is usually charged negative, and the top is positive. And that's just because the electrons are sheared off the molecules and resides at the bottom. Because the bottom of the storm cloud is negative, on the surface of the Earth, this is the Earth now, on the surface of the Earth, it's going to push away the electrons on the surface of the Earth. So you're going to be left with only positive charge on the surface of the Earth. Okay, so that is what storm clouds do. Okay, again, the storm clouds, because of how they form, the bottom is going to be negatively charged and the top is positively charged. And the negative charge on the bottom, which is electrons, going to push away the electrons from the surface of the Earth. So the surface of the Earth is going to be positive. Okay? So that's one of the first thing that happens. Then after you get your negative, the storm cloud, the bottom of the storm cloud is negatively charged and the top is positively charged. The Earth, because the negative charge storm cloud going to push away the electrons from the surface of the Earth. So all you're going to have is positive charge on the surface. So how you get the polarization of the storm cloud is because of collision of ice particles in the cloud. when you have collision of the ice particles, the electrons are sheared off and they reside at the bottom of the storm cloud. And the top of the storm cloud is positive. So the negative charge at the bottom of the clouds going to induce positive charge on the earth, because negative charge is going to push away all the negative charge on the surface of the earth, only leaving positive charge. Okay? So once the charge builds up in the storm cloud, the charge going to gradually build up, build up, build up. Then what's going to happen is you're going to get polarization of the air around the cloud. So the region around the storm cloud going to get polarized. Okay? And once it gets polarized, then it becomes conductive. And then you can have the electrons moving from the storm cloud to the earth, because the air around the storm cloud becomes ionized. Okay? And then you get, these are what we call leaders. Okay? So you get the electrons can move from the storm cloud through the conducting air to the earth, and we call these leaders. Now you can get what we call streamers. Streamers are positive charge from the earth. So positive, once these storm cloud becomes highly polarized and highly charged, then it will actually pull the positive charge from the earth's surface, and those are what we call streamers. And the leaders and streamers combine to give you the lightning. So the two join and create a channel through which lightning strikes. So again, we have the storm cloud, and because the ice particles are colliding with the cloud, it polarizes the cloud. So the bottom of the cloud becomes negative, the top becomes positive. The negative bottom of the cloud is going to push away electrons from the surface of the earth. So you're just going to have positive charge on the surface of the earth. The air around the bottom of the storm cloud is going to become ionized. And as a result of that ionization, it becomes conductive. So that means it can conduct charges to the earth, and that's what it does. That's what we call leaders. But once the storm cloud becomes highly charged, then you have a lot of negative charge on the bottom, and it actually pulls up the positive charge from the earth's surface. That's what we call streamers. So when the two meet, you get what we call storm cloud. Lightning. Okay, so. And you can see the lightning, and sometimes it go all the way down. Okay, now we're going to discuss lightning rod, because lightning rod is protective, because lightning can the charge in a lightning strike is usually very, very tremendous, and it can damage, it can kill people, it can damage anything on the earth's surface. So the concept of lightning rod came about because of Ben Franklin. So Ben Franklin discovered and developed the lightning rod. And the lightning rod consists of a pointed metal pole. And this pointed metal pole is connected to what we call a grounding rod by a thick copper cable. And the grounding rod is buried below the earth. Basically, what you're trying to do is divert the lightning from, say, a house or a building to the ground. So instead of the lightning striking the house or the building, you divert it through this lightning rod to the earth. Again, the lightning rod consists of a pointed metal pole. it is connected to a grounding rod by a thick copper cable, and the grounding rod is buried in the earth. So it looks something like this. Okay, so your pointed metal pole. Of course, you have your thick copper cable, and then the grounding rod goes all the way to the earth. Okay, the lightning rod divert the lightning to the ground. So instead of going to the house, it diverts it. So again, you have the lightning rod, you have your conducting wire, and then your grounding rod, which it goes into the earth. So the lightning will preferentially travels down the lightning rod, down the wire, and into the earth. Okay. Again, it divert the lightning. So we spoke about the electric field inside a conducting surface. It's zero, and the practical use for that is to protect expensive electrical equipment. You put it inside a metal uh, box, and it will be protected. We talk about storm clouds. What is storm clouds? How storm clouds are formed, and then lightning, and then the lightning rod. So that concludes static electricity.